Now I'm sharing my screen, of course. The first lecture, as we were following the curriculum we were watching with you, is based on the FR Physics notes by Dr. Abdullah. It might contain some basic information, but it's very important information. I will try, God willing, during the lecture to make the topic not boring. I know that this is physics information, which can be dull, but I will try to connect it a bit with the application part so that the information becomes more tangible for you and you can better understand it. Is the sound clear and is the screen clear? Is everything clear for you? Any problems? Also clear? All right, let's get started. In our first lecture, we are supposed to talk about basic science regarding the physics of medical imaging. Maybe this first lecture is because I need to introduce someone. Maybe this first lecture Well, the first lecture, as I mentioned to you, is a bit of information about physics, but I see it as very basic and very important information. For you, whether a person works in medical imaging or not, they must be aware of this information. Our outlines today about atomic structure, radioactive decay, and electromagnetic radiation are three main points that are very important. We will discuss them in detail and review the essential information that you need to understand well for each of these items. All right, Professor, could you please mute the sound? Is it possible for us to mute only the microphone at this moment? The reason we need to do this is because there is a lot of background noise that is causing a disturbance. By muting the microphone, we can ensure that the noise does not interfere with our current activities or conversations. This will help us maintain a clear and focused environment. We all almost hear about the topic of atomic structure. It's something we all hear about. We hear that any material in the world is made up of an atom, which is a single atom. Inside this atom, there is a nucleus, which contains neutrons and protons, and around it are electronic shields. Inside the nucleus, there are neutrons and protons, and these electronic shields contain electrons. Are protons found in these electronic shields? This information, I believe, is tangible and known to all of us. The nucleus itself contains protons, which have a positive charge, and neutrons, which are neutral. Surrounding the nucleus are the electrons, which of course have a negative charge. They are located in electronic shells, meaning around the nucleus itself. I have several orbits, each with a certain number of electrons present. These fill or occupy the electronic shells according to the atomic number of the atom when discussing atomic structure. Let's forget it, because I'm just entering, okay? Any atom, I mean things called atomic number, and I mean things called mass number. The atomic number is Z, and the mass number is A. As I mentioned, the atom has a nucleus, and the nucleus contains protons and neutrons. The summation of the number of protons and the number of neutrons is referred to as the mass number. The atomic number is the number of protons and the number of electrons present. The X is simply the symbol for my atom or my element, whether it is chlorine, fluorine, zinc, or whatever the material is. It has a specific symbol, and this is found in my periodic table. So the whole idea is what the Z number is, what the mass number is, and what their importance is. The Z number is responsible for the chemical properties of that material, especially its chemical characteristics. The mass number is responsible for, in its dynamic form, If I have two atoms or two substances that have the same atomic number, that means I cannot separate these two atoms chemically. Why? Because they have the same chemical properties. They might differ in their physical properties, but since they share the same atomic number, I cannot treat them chemically. Now, why am I saying this? Because later I will explain to you the importance of this point in the production of radionuclides or radioactive materials. So when I reach this point, is it clear or is there a problem? Doctor? The neutron and proton are called nucleons. Now, when we hear the term mass of the atom, we often ask where it is centered or concentrated. In the nucleus. We always hear this. Because when they conduct a weighing process or check the weight of the atom, they take an atom like the carbon atom, specifically carbon 11 or carbon 12. This carbon atom contains 6 neutrons, 6 protons, and 6 electrons. Then they start to look at the weight of each particle. How much does a proton weigh? How much does a neutron weigh? And how much does an electron weigh? They found that the proton is equivalent to 1 atomic mass unit. So what is this atomic mass unit? It is the unit of weight for these particles, which they called 1 atomic mass unit. As for the neutron, it has the same weight or mass. Therefore, both the proton and neutron have equal masses, each considered to be 1 atomic mass unit. The electron, however, has a mass of 1/1800. A mass unit means a very, very, very small mass compared to the neutron and proton. So, it is concluded that the mass of my atom is concentrated in its center, which is the nucleus. Now, take the carbon atom. As a good example, it has 6 protons, 6 neutrons, and 6 electrons. It started weighing all the atoms present in nature relative to the carbon atom and named 1 atomic mass unit as 1/12 of the mass of the carbon atom. So, when I say a neutron is 1 atomic mass unit, it means it is 1/12 of the mass of carbon. Now, what is the charge of the neutron? It is 0. The charge of the proton is +1, and the electron is 1. The symbols are: the neutron is represented by N, the proton by P, and the electron by E, which has a minus charge, as we can see. As I mentioned, if I have the carbon atom, it has 6 protons and 6 neutrons, which means it has a mass number of 6 atomic mass units for neutrons and 6 atomic mass units for protons. That's why I chose the carbon atom or selected the carbon atom as a reference or reference atom for me to perform the weight calculation of the atoms present in relation to the carbon atom. Are there types of electrons that orbit around your nucleus? Yes, of course, there are types. These types include something called free electron, something called bound electron, and something called valence electron. So I have 3 types: free, bound, and valence electron. Now, I mentioned that around the nucleus there are electronic shells, right? The mass of the atom is concentrated in its nucleus, which has a positive charge because it contains protons. The closer the orbital is to the nucleus, the more the electron in that orbital, which is close to the nucleus, is bound to it. Therefore, the innermost electron that is close, or in the electronic shell that is very close to the nucleus, is called a bound electron. This electron is strongly influenced by the attraction force of the positive nucleus. So in this case, I call it a bound electron. Where is the bound electron? The bound electron is in the innermost shell of my atom. Now, if I want to remove this electron from the atom, I need to overcome the binding energy. You need a very large amount of energy to overcome this attraction force. This attraction force is the energy required to overcome it, known as binding energy. Binding energy is the energy required to overcome the pull of the nucleus and to release the electron from the shell. You need to overcome the attraction force of the nucleus on this electron, so you need energy. For example, if we assume that this binding energy is, say, 50 electron volts, then you need an equivalent or equal amount of energy to remove or release this electron from the atom. Now, if I have my atomic number, Z number, increased, meaning the number of protons has increased, then the positive charge has increased. Therefore, the positive charge of the nucleus increases, which means that my binding energy will also increase. That's why the higher my atomic number, Z number, the greater the binding energy affecting the electrons, and the more energy I will need to remove this electron from the atom. Now, the free electrons are the second type I was talking about. They exist when I take an atom and bond it with another atom, forming a molecule or creating a lattice or crystal structure. This structure is formed with me, and some of the electrons take this shape. Here, for example, if I have a group of atoms that form a lattice or a specific structure, the free electrons are present in this way. They are not found in the outermost shell or the outermost layer of electrons, but they are responsible for the electrical conduction and thermal conduction of the materials. The free electrons are always present in the lattice structure of the material itself and are responsible for thermal and electrical conduction. Now, regarding the valence electrons, the outermost shell, or the last orbital around the nucleus, contains electrons that I refer to as the valence shell. This valence shell is responsible for the process where, for instance, you want to bond with another atom. This is what is called the valence electron, which is involved in the process of gaining or losing electrons. The valence shell, or the valence electron, is what is responsible for this process. As I mentioned regarding binding energy, you will find that for every atom or material with a high atomic number, the binding energy required to remove the electron increases because the atomic number has increased, due to the increase in the number of protons, resulting in a higher positive charge, which increases the attraction force on the electron. The further the electron shell is from the nucleus, the weaker the binding force or the attraction force acting on it becomes. There is an inverse relationship between the binding force and the square of the distance between the nucleus and the electron. The farther away it is, the less the binding force or the effective binding force becomes. Therefore, you will find that the binding energy required to remove an electron from the K shell is greater than the binding energy required to remove an electron from the L shell, which is greater than that from the M shell. So this is regarding binding energy, bound electrons, free electrons, and valence shells. Here is a comparison that clarifies the difference between valence electrons and free electrons. As I mentioned, valence electrons are those found in the highest energy levels of atoms, while free electrons are not bound to any atom, but are present in the conduction band. Valence electrons are responsible for chemical interactions or chemical bonds. Essentially, a chemical bond is formed between one atom that loses an electron and another atom that gains an electron, resulting in a bond between them. The free electron is not involved in chemical bonding. Valence electrons cannot conduct heat and electricity, but free electrons are responsible for the conduction of heat and electricity. The number of valence electrons present in an element is distinctive. For example, the electronic distribution of sodium shows that it fills up to 8 electrons, and the last one has 1 electron. Therefore, the last one, which is filled with 1 electron, distinguishes the sodium element, which has an atomic number of 11. 11, that's right indeed. Here it specifically refers to the particular type of atom that is present. As I have previously mentioned, it also distinguishes the number that is actually present and the property of the atom that is currently present. So far, doctors, is everything simple, or are there any potential issues or perhaps any concerns? Dr. Bassett explains the difference between ionization and excitation. When you say, I have an ionized atom or an excited atom, what is the difference between an ionized atom and an excited atom? Here, you will find an explanation that clarifies this. If I have an atom with a nucleus, which is the core, and there is an electron, this electron has gained energy. This energy is sufficient to move the electron from its current energy level to a higher one, but not beyond the atom. it has gained energy, which causes it to move from this level to a higher one. In this case, if this electron remains in the higher level for a while and then returns to a lower level, it will start to lose the energy it has gained. The energy he gained is in the form of a X-ray. I call it characteristic X-ray. All right, so I will keep this information in mind because we will need it later. The X-ray is not just artificial. Now, if an electron moves from one energy level to another and loses energy in the process, this energy is called characteristic X-ray. If my atom gains this energy from the nucleus, as we will discuss later, there will be energy emitted from the nucleus with a certain amount of energy that can excite this electron from the inner shell to the outer shell, for example, the next shell. Consequently, it will emit an X-ray. In this case, it becomes a natural source of X-ray, meaning that our usual understanding of X-ray is that it is produced by something artificial, like having a cathode, an anode, and an X-ray tube. However, you might discover that there are some elements in nature that emit X-rays. This is what is meant by excitation. Now, regarding ionization, if the orbital electron gains energy, it can be ejected from its orbital. So it is negative, and thus the atom itself turns into a positive ion, forming a negative ion, which is the electron, and the positive ion, which is just the atom itself. This process is called ionization, or ionization in this case. The meaning of ionization is that the electron has exited its orbital due to gaining energy. This energy is sufficient to free the electron and overcome its binding energy, and it also gives it kinetic energy, allowing it to move. In this case, I call it ionization. This is the difference between ionization and excitation, right? If I told you that this lecture is essential, we will not speak in sequence, but we will provide some important information that will benefit us in the course, God willing. I would like to ask you a question in the spirit of conversation. If I were to ask you now, have you heard about Well, if I were to ask you a very simple question right now, why are atoms radioactive? Why do atoms become radioactive? For example, we hear about having a radioisotope. What makes these atoms radioactive while there are other stable atoms? What causes some atoms to be unstable and others to be stable? Does anyone have an idea?
Because the atom is at a higher energy level, it will lose some energy to reach a higher energy level.
The atom is at a higher energy level, so it transitions to a higher energy state. The question here is what makes it a higher energy level? Let's delve a bit into the details. What makes the atom? What makes, for example, the atom itself unstable? How many protons are there? Well, don't we say that inside the nucleus there are protons and neutrons? Right. Okay, so what is the charge of these protons? Correct, right? Is it normal to place protons or all positive charges together in the same very, very, very small space without causing repulsion? No, of course, that is not logical. There must be binding energy or strong nuclear force. This strong nuclear force is what creates the attraction or binding of the components of the nucleus, the protons present. Unless there is a repulsion force that occurs, or the electrostatic force between the protons is greater than the binding force or the strong nuclear force, in this case the atom becomes unstable. However, as long as the nuclear force or the binding energy between the protons is sufficient to keep these protons together without repulsion occurring, I maintain the stability of the nucleus. This balance depends on the equilibrium between the number of protons and the number of neutrons. As long as there is a balance between the number of protons in the nucleus and the number of neutrons, I wouldn't say they are equal, but rather in balance, This leads to the stability of the atom. If there is a disturbance or an unbalance in the number of neutrons and the number of protons, meaning I have an excess number of protons, a significant increase in the number of protons, therefore the repulsion force increases, making the atom unstable, and the nucleus wants to become stable, which leads to a process called decay or nuclear decay that we will discuss shortly. So this is a concept, right? But what makes the nucleus unstable if it has an excess number of neutrons, considering that neutrons are neutral and have no charge? I understand your point, and it makes perfect sense that protons, due to their positive charge, if their number increases significantly in the nucleus, will cause repulsion. Consequently, the atom won't be able to maintain stability, thus becoming unstable. This reasoning is logical and very clear. So if the nucleus has a large number of neutrons, as I mentioned, its instability has two cases, either an excess number of protons or an excess number of neutrons. The number of neutrons is greater than the protons, or the number of protons is large. The concept of having a large number of protons is understood, but how should I understand a large number of neutrons? How does it lead to repulsion? Does anyone have an explanation, doctor? The whole topic is quite simple when it comes to nuclear physics, just so you understand, but not more than that. The proton itself contains particles inside it, and these particles are called quarks. In the proton, there are three particles, two particles called up quarks, and one particle called down quark. The up quark has a charge of plus 2, 3, while the down quark has a negative charge of 1, 3. So when I add these charges together, I get plus 2, 3, which means I have plus 4, 3 minus 1, 3. Then I add the charges together, and then I proceed by saying plus 2/3, and then plus another 2/3, which ultimately gives me a total of 4/3. And then finally, minus 1 out of 3, which is for the down quark. The total charge is 3 out of 3, which is plus 1. That's why the charge of the proton is plus 1. So where did the proton get this charge from? It results from the sum of the quarks that are inside the proton. This sum of the quarks inside has a charge of plus 1. Now, for the neutron, you have two down quarks and one up quark. The up quark, as we said, is plus 2 over 3, and the down quark is minus 1 over 3. So, plus 2 over 3 minus 1 over 3 minus 1 over 3 gives you a total of 0. That's why the charge of the neutron is 0. Now, what is the relationship of this to instability? The relationship to instability is that there is an arrangement of neutrons and protons inside the nucleus that maintains this stability. When the number of neutrons increases, you have up quarks and down quarks present inside the neutrons, which have charges. This leads to repulsion occurring, or the arrangement becomes unsuitable for the stability of the nucleus, resulting in a repulsion force between the quarks inside the neutrons. This is why, within atoms, the excess number of neutrons causes instability, and the excess number of protons also leads to instability in atoms. As we mentioned, there is a specific group of neutrons with protons. If the number of protons increases, this affects the internal quarks and the charges between them, which enhances the stability. If the number of protons increases, it becomes clear that this will affect stability. Now, if you are in this atom and you have an excess number of protons or an excess number of neutrons and you want to achieve stability, what do you do? For instance, if I currently have a large number of protons causing instability and I want to stabilize the atom or the nucleus, what should I think about? You would say, okay, I will convert a proton into a neutron, which reduces the number of protons and increases the number of neutrons, leading to some balance and thus stability. This is indeed what happens when an atom has an excess number of protons. It starts to convert protons into neutrons. Conversely, if the atom has an excess number of neutrons, it does the opposite and converts neutrons into protons. In order to reduce the number of neutrons and increase the number of protons, a balance is created between the protons and neutrons, leading to a state of stability. This is what I call decay. What does decay mean? It means that when an atom is unstable and has a large number of protons, it wants to stabilize itself by converting a proton into a neutron. As a result of this conversion, from proton to neutron, a type of radiation begins to be emitted. This type of radiation, resulting from the proton to neutron conversion, produces something called a positron, which is a particle. For example, in the case of the element fluorine, it interacts with this. In the case of the positron, for example, an element that is labeled with the fluorine-18 isotope has an excess number of protons in its nucleus. To achieve a stable state, what it does is convert a proton into a neutron, transforming into another element in the process. Then it emits a positron, which later has subsequent interactions that it interacts with